Hello. So today we are going to talk about surface plasmon polariton. So far in the lectures we have discussed about volume plasmons, which was related to the frequency omega p that was intrinsic to the material. Now we are coming to this surface plasmon systems. Now ideally plasmons are oscillations, quanta of oscillation of the plasma, and in practical sense if you look into it, it only makes sense when it is coupled to a radiation. So it is coupled to a photon. So a plasmon, a quasi particle consisting of a plasmon, here in this case it's surface plasmon, plus a photon is defined as a polariton. Okay, so as the name suggests, these plasmons are located at the surface of a metal or a conductor. Now when we talk about it, so typically this SPP, as it is normally known, it is the coupling of electromagnetic radiation, of an electromagnetic radiation, which is the photon, as I have told you already, with oscillating charges on a conducting surface. Now in this case, what conducting surface can you think of? You can think of a dielectric, so basically to get this conducting surface, one needs to have an interface, and the way it is done is it's a dielectric conductor interface. So in real sense it could be just a surface of a metal, so the metal forms the conductor while air is your dielectric. So we can have surface plasmons, or you can deposit a dielectric on a metal and create your own interface depending on the dielectric constants you are looking for. Fine. So now so when we have a interface of this sort, so let's say I have a dielectric like this, and underneath I have a conductor. So this is my conductor and this is the dielectric. So we do have this interface, and this interface is where the surface plasmons will be created. Now to create them, the way it is done is, of course, for the surface plasmon polaritons, SPP, we need an electromagnetic wave, we need photons. So the way we will do it is, you have to shine light where the propagation direction is in the plane of the interface. So if you look into this, the electric field associated to this structure now, so I may draw the axis here. So let me just get another color so that it doesn't get confused. So we can have this. Anyway, so this is, I will call the x-axis, this direction y, and vertically up is the z-axis. So x and y form the plane of the interface, and z is normal to it. The beam is propagating along x, so x is the propagation direction of the electromagnetic wave. Now, so how do we write the electric field associated to the, so electromagnetic wave propagates along x. Now hence the electric field, which will be a function of position and time, associated to the EM wave is can be written as some magnitude which is a amplitude which is a function of z. I'll come to this point, and then we have the standard exponential I kx minus omega t. Okay, so where kx is the propagation vector or the wave vector, in our case it is along x-axis because the wave is propagating along x, and omega is the frequency of the light field. Now coming to this Ez, what is this Ez? Now electric field, the amplitude of the electric field is said to be a function of z, which means that as you go along the z direction, so if we go plus z or minus z, so if we go into the dielectric or if you go into the metal in these directions, you have a change in the amplitude. So this is actually defined by evanescent waves. Evanescent fields rather. Now what are evanescent fields? Evanescent, so whenever you have electromagnetic radiation which is confined to a region, then the fields which are not allowed, the direction in which the field is not allowed to propagate, in that direction you start seeing exponentially decaying field. Okay, so here for example along the z direction the wave is not allowed, so the wave is propagating along the xy plane, so it is not along the x-axis rather, it is not allowed to propagate along the z-axis. So along z the field doesn't propagate, but it has a variation in the amplitude which is defined by evanescent waves, and typically it is of the form of exponential some minus alpha z. So it's an exponentially decaying field, some E naught exponential alpha z. So these are called the evanescent fields, where we have confined the electromagnetic wave in the plane of the interface, and so if we look in the z direction, the beam cannot propagate while the amplitude decays as a exponential function. So if I look into this once again, so if I look into the cross section of the dielectric, and the lower part is your metal, so the way we name it is this part, the interface is at z equal to 0, the dielectric is for z greater than 0, and for z less than 0 we do have the conductor, which is your metal or whatever. And what else do we need to assign? We have a dielectric constant which we call EC for the conductor, and epsilon d which is the dielectric constant of the dielectric medium. Now if I plot this function, so if I say I have z axis, this is the z equal to 0, and this direction it is the electric field magnitude, then at z equal to 0 let's say the field is some E naught, so it will be decaying exponentially within the metal, and it will also decay exponentially within the dielectric, but both will have a different decay constant. So for example, in the dielectric side it will decay, let's say, as kdz, and in the metal side it is exponential kcz. Mind it, its z is negative, that's why it will be a positive term. So the other two parameters that we need to define is the evanescent wave decay constants, which is basically kc here and kd in the dielectric. This is how we will define the problem in this situation. So next day we will continue with the formulation of this problem. Thank you.